Okay, so last time we were talking about arc length, right? And in particular, we talked about the idea of using arc length as a way to parameterize a curve. So the way I like to think about this, my favorite metaphor on this is thinking about a road and how you can parameterize a road, keeping in mind the idea that parameterizing we usually think of as basically tracing out the curve, right? Position is a function of time. If you drive along a road, your position on the map as a function of time as you drive, as you take that road trip, is a parameterization of the road, right? But so what we mean by arc length parameterization is don't think of the location on the road as a function of where you are at a particular moment in time. Think of it as a parameterization by mile markers on the side of the road. Right, and the thing about it is that's intrinsic to the curve, right? It's intrinsic to the road. Doesn't matter how fast you drive down Highway 40. Mile marker 268 is always in the same place, right? So it's a canonical parameterization, you might say, and again, it's intrinsic to the curve, not to the driver. Okay, so we talked about how to do that. In particular, you can compute this arc length distance. Take any existing parameterization, whatever, right? And at any given moment t, representing where you are at a particular point, at a particular moment, you can compute, well, how much distance have I traveled from wherever I started, right? And we have a formula for that distance. Arc length along the curve. We talked about that last time. And keeping in mind that t, again, already has a role. T is the parameter in my original parameterization. So I can't write this integral in terms of, I can't say as t goes from 0 to t. That doesn't make any sense. T is already a thing. You can't make it a different thing. Right. So with that in mind, we have to choose a different dummy variable to be our parameter for our integral, right? And arbitrarily, people like to use the lowercase Greek letter tau. Sometimes you don't have to. If you want to use q, totally fine, not a problem, right? Any parameter you want. Here, I'm using tau just cause. So once you have this function, once you have here it is. Once you have s as a function of t, notice you can invert that function. You can solve then for t as a function of s. You just, whatever the formula is for s as a function of t, solve for t. And plug in that formula for t into there, and what you will have is position as a function of s. So position as a function of distance traveled. Location on the road as a function of mile marker. Right. Okay. All right. So that's the big idea. I'll show you an example in a minute. Again, why would we ever do such a thing? What an arbitrary thing to do. Well, again, it's natural. It's intrinsic to the curve. It's a canonical parameterization. Also very nice and useful when you're trying to prove certain facts in geometry is the fact that this is a unit speed parameterization. The magnitude of derivative with respect to s is 1. The reason why, and an easy little algebra to see, here's the chain rule applied to position as a function of s, which is a function of t. Right? Just write down the chain rule for position as a function of s, which is a function of t. Write that down. Here it is. And take the magnitude of both sides, and, well, this says, what is the magnitude of my velocity? This says distance per unit time. They're both speed. Right? So these two things are equal, and that means that this, namely the velocity from the arc length parameterization, is 1, and thus unit speed. So easy little argument there. So it's a nice thing, and if the opportunity presents, it's nice to have an arc length parameterization. Tragically, it's in practice, kind of a pain at best. So I'm going to show you an example. And in fact, to be clear, this example I'm about to show you, this is I don't want to say best case, but I've gone to some trouble to arrange for some algebra to work out really nicely in this case. Anyway, that said, let's plow through it. Here's a parametric curve, and let's compute arc length as a function of t. All right, this is the formula from above. And let's crank it out. Well, you got to take the velocity of the parametric curve, blah, blah, blah. Take the magnitude. The magnitude, of course, is the square root of the sum of the squares of the velocity. And multiply out the under the radical there, and you get this. And here's where you can see how conveniently I arranged this to be. This 4 tau squared turns this minus 2 tau squared into plus 2 tau squared, which makes altogether this a different perfect square. It's just 1 plus tau squared quantity squared. Did everybody see what happened? There's a slick move, right? I mean, again, I had to go to some trouble. Usually this will not happen, right? So usually what you're going to have is a square root of a not very nice polynomial. And so you see why this is, very often you just can't, arc length parameters is going to require you doing a ridiculous integral. So in this case, again, I rigged it up so it'd work great, and look at this, got a nice easy integral, and it's an easy antiderivative to find, and yet still I have an impediment. Because recall, in order to do an arc length parameterization, you're going to have to solve for t. And in this equation, I can't. It's cubic. So even here, it works out poorly. So, anyway, like I say, it's, rarely is this a convenient thing to do. But as a theoretical construction, as a tool for again, proving theorems, it's very useful. Okay. So I just wanted y'all to know what the arc length parameterization is. And with that, we're going to move on now to section 3.3. So, new objects of study that we're going to talk about here, vector fields. These are going to be a big deal in the course. We're going to basically, there's some important mathematical constructions that we'll see in chapters 6 and 7 that are going to be the main thing we're going to study in chapters 6 and 7. It's going to be a certain kind of integrals. They're going to specifically be integrals that involve these things called vector fields. And those integrals are going to turn out in y'all's futures to be extremely important in engineering and physics and this kind of stuff. They're just crazy important. So this is a new critical object of study. Vector fields themselves, by the way, also very important to understand even outside of the chapters 6 and 7 powerful results. Just because they're a way to represent certain kind of physical phenomena. So anyway, let's dive in. Here is a kind of a definition. Vector field on Rn is a function from Rn to Rn. Algebraically, that's what it is. But this is not how you think about it. The way you think about a vector field is in how you interpret the participants in this function. So specifically, whatever comes out of the domain, the input, you're going to view that as a point in Rn. Specifically a point. Now it could be R2, could be R3, whatever. But the inputs are to be interpreted as points. The outputs over here, also Rn. By the way, these do have to be the same dimension. Rn to Rn. Got to be the same. The outputs we do not interpret as points. Very importantly, the outputs we interpret as vectors, which of course we represent with arrows. So what you have here, what I've drawn there is a sort of an example of how we view one point that goes into this function and what its output is, and this is how we sort of think about it. I think of this output vector, the field vector we call it, as being an arrow at the input point. That's where I put the tail of the output vector. So you get pictures kind of like this. Kind of weird, right? Odd choices. Everybody see how I get these kind of pictures? Questions? Feel free. Okay. You might now then start to see why this is actually a pretty natural thing to want to do. Why would I be interested in these things? Well, I mean, what image comes to your mind when you see, for example, something like this, and I see a fluid flowing? You know what I mean? And this is telling you, if you have a fluid flowing around, all right, well, for example, at this point, what is the velocity of the fluid? Take, for example, the air in this room. Right, the air in this room is a fluid, and however slowly, it is flowing a little bit. The air conditioner is on, despite my best efforts, and I'm talking. That's making noise. I'm waving my arms around. Right, the air is moving a little bit. So we could talk about what is the vector field that describes the movement of air in this room by pick any point, whatever point you want to talk about. At that point, at a particular moment, the air is moving with a certain velocity. There you go. How does that strike you? Everybody okay with that? All right. Okay, so there's going to be more uses than that for vector fields, but a couple of examples just to get the ball rolling. So let's look at this one right here at point x comma y, and keep in mind this could be any point in space. Right? For any point in space, the field vector for this vector field 2, 1. Notice it's a really boring function. It doesn't even depend on x or y. It's a constant. It's always the same, right? So it's a constant, what we call a constant vector field. And if you draw the vector 2, 1 as the field vector at every point, then you get this picture right here. So this is what a constant vector field looks like. Does everybody see it? Everybody's happy? A little counterintuitive that it's literally a constant vector field, and yet we view this as representing something that's moving. Right? This is representing a moving fluid. So anyway, it's just weird. All right. Here's another example. Let's look at this one right here. F of x comma y is x comma y. That looks pretty basic, right? I think this would be nice and simple. It's kind of weird how this turns out. Again, you got to think through the picture. At a point x comma y, keep in mind the inputs count as points, right? And now a quick tangent, a quick aside. Don't forget, whenever you have a point, there is the associated position vector for that point. So that's just an aside. Now, that noted, let's see here. What is my field vector? Well, it says right here the field vector is the same as the input point, or more intuitively satisfying. The field vector is the position vector for the given input point. Right? And so what that means is that this field vector, well, again, it's the exact same vector as the position vector. So let's see here. I'll use green. This being equal to that manifests in the picture by that equaling that. Everybody on board? And so now you got to visualize, okay, if I were to do this kind of thing here at every point in space, that means that at every point in space, I'm going to have the arrow go radially outward from the origin with magnitude equal to how far it is away from the origin. Then I claim you get a picture that looks kind of like this. What do you think? Always radially outward. The farther you get away from the origin, the longer the field vector arrows are. Okay. Cool. All right, here's one. Let's try to understand this thing right here. Again, we're going to try to just have to notice, maybe we'll get lucky here, but at a point x comma y, so I don't know, let's consider such a point like this. The field isn't the position vector, but you do notice that the field vector and the position vector have some things in common. That it's x's and y's and stuff, right? So they seem to have a relationship. You notice pretty quickly, by the way, they have the same magnitude. X comma y and negative y comma x, same exact magnitude. You might also eventually notice dot product is 0. So these are, the position vector and the field vector are perpendicular and with the same magnitude. And not hard to persuade yourself at that point that what we have looks something like that. Again, notice what I've got drawn here. The field vector and the position vector are perpendicular with the same magnitude. You know, limited by my artistic ability here, but that's what I was trying to draw. And do that same thing at every point in space, and you can persuade yourself, I think, color choices, that this vector field looks like this. Everybody buy it? Again, this, you can think of this as a fluid flowing, and if so, you might think of this as a stirred pot. How come it's stirred counterclockwise? Well, because if you look at, which direction does the position vector get rotated to become the field vector, it's counterclockwise. And that's a linear algebra thing. And again, I remind you, powerful results in linear algebra, basic but powerful results in linear algebra that we're going to use a lot in this course. Linear transformations, such as rotations, are represented by matrices whose columns are images of standard basis vectors, which I can usually determine by geometry if they're nice linear transformations. So again, make sure that you can fill in those details. We saw an example of that on the exam last week, by the way, and you want to make sure that you can do that. Okay. Come to office hours if you have any questions on how to do that stuff. Happy to talk about it in office hours. Okay. Alrighty. Everybody all right? Questions? Okay, here's one. I mentioned this one just because it's going to come up a lot, especially when we get into chapters 6 and 7. But this one is physically natural in that this is what gravitational fields look like. Kind of a big deal, right? It's also what electric fields look like, which again, pretty big deal. And if you're not an astronaut, probably more important than the gravitational fields, right? So, very important to understand this vector field, which you've noticed I've written in kind of a weird way. I haven't written it in terms of coordinates. I've written it with a vector notation. This is the formula, but I prefer to think of it as this same exact formula, of course, just kind of factored around in a different way. The advantage being that this part here is clearly a unit vector. And so you can see very evidently in how this is written now what the magnitude is. The magnitude is what we call an inverse square magnitude. The reciprocal of the square of the distance from the origin being where the particle is assumed to be located in this example. So radial, because of the fact that the unit vector points radially outward away from the origin, right? And inverse square because of the magnitude. Okay, so radial inverse square. You may wonder why I drew these arrows here as being inward, and I drew them inward because I was thinking about gravitational fields as I drew this, and of course gravity goes inward as opposed to outward. And so in this example, this constant here would just be negative. Everybody happy? All right, so there's a bunch of examples of vector fields. Here's another really important example of a vector field. It's at a glance doesn't look like it's a vector field. Gradients. We've already talked about gradients before. Let me get out of the red. It's a very scary color. Gradients are a formula, and they give you a vector, and it always points uphill on the graph. This is all old news, right? We've established this some days ago. And so all I'm really going to add to this to make it relevant to what we're doing now is point out that you can think of that as a vector field. We didn't previously because we didn't know what vector fields were, right? But now that we do, innocent observation, if you have a real valued function, such as this right here is a real valued function, then the gradient is something that you can write down. Formula you can write down. There it is. 2x comma 2y, and check it out. It's a vector field. For any point x comma y, I get an associated vector for which I have a formula. So how about that? It's just a different point of view on how to think about the gradient. The gradient of a real valued function you can think of as being a vector field in the domain of that function. So now it remains that it always points uphill on the graph, right? So wherever you might happen to be, say that point there in the domain, right? You can ask, well, what is the associated point on the graph? The associated point on the graph is like there, and if this were a, well, it'd be a weird mountain. If this were a volcanic cavity or something, that I was a sinkhole maybe that I was hiking around in. Which way is up? Well, uphill would be, up the side of the thing, and so which direction in the domain does that point? Well, that way, which you'll notice is the direction that this gradient points. So just like previously, the gradient always points uphill. Here it's a vector field that always points uphill. Everybody happy? Yes?
Does that vector field only rest on the xy plane?
Yes, that's right. So the gradient of a real valued function is always a vector field in the domain of whatever your function is. And here we have a function that's it's defined on R2. So that's right. This is a vector field in R2. Absolutely. Good question. Anybody else? All right. Okay, let's talk about terminology a little bit. This is a little bit frustrating for me that the world doesn't do things the way I think they ought to. Anyway, I'm going to make the case first for the way I think the terminology should go, and then I'll reveal what the more common terminology is. So suppose we have a real valued function, and we take its gradient, right? So taking the gradient of a real valued function, and that results in a vector field. Well, the thing that comes out of the gradient operator, no surprise, we call it the gradient of the input. And now turning that around backwards and think in terms of, a similar situation when you take a derivative of a function to get another function. When you turn that around backwards, the input we think of as an antigradient of the output. Right? Just like with derivatives, and you go backwards, it's the antiderivative. So I think this is hard to argue with as being natural and transparent and clear terminology describing what this thing is over here. I like to call it the antigradient. So anyway, you're going to hear me say antigradient a lot in this course. Now that said, sadly, that's not the most common term. In physics circles, this gets called the potential function. And the reason why is because this little scenario here where we have a function and we look at its gradient vector field is closely related to a situation in physics that comes up a lot. And that is if you have certain kinds of forces, gravitational forces, for example, you can talk about potential energy associated with that, gravitational force. And by the way, if you don't know this physics, if you haven't seen potential energy before, it's not a big deal. You don't have to know any of this physics. This is just context in case maybe you do. So there's a temptation, an oversimplification to say that force is the gradient of potential energy, but it's not. It's the gradient of the negative of the potential energy. And that minus sign, I mean, the easy way to sort of see that in real life is think about just gravitational potential energy here at the surface of the Earth, right? And potential energy gets higher the higher up you go. The formula for potential energy is like something times Z. So if you think about it, the gradient of potential energy points up. Gravitational force pulls down. They're just opposites. The gradient is not equal to the force. The gradient is the negative of the force. So that's awkward. So there's two reasons then that I don't like this. Well, that's an overstatement. Two reasons that I don't prefer this term potential function in place of anti-gradient. For one thing, the motivating metaphor has a minus sign that's conveniently been ignored. Right? That's confusing. I find that unavoidably confusing. So I don't like it for that reason. The other reason is, believe it or not, sometimes in math we're doing things that are not necessarily about physics. And so I don't like terminology when it can be avoided. I don't like terminology that's narrow from a particular application. And y'all have heard me gripe about that previously with direction of steepest descent. Well, it assumes we're looking at a graph. We're not always looking at a graph. Direction of fastest increase always makes sense. So anyway, that's my spiel about terminology. You're always going to hear me say anti-gradient instead of potential function. Questions? Everybody's happy. Alrighty. Okay, so let's see here. So now we've seen some examples now that vector fields can represent forces, right? Gravitational forces, electric field, electric forces, right? So, all right. What about these other Are there any other standard interpretation of vector fields? You may recall the very first one that I kind of, conjured looking at our very first picture of a vector field. I said, doesn't that look like the flow of a fluid? And absolutely. We definitely use vector fields to represent flows of fluids. And fluid flows are a big deal. Airflow, ocean currents, how is pollution moving around in wherever it may happen to be moving around. Components of the atmosphere, where's the ozone going, this kind of thing. So there's lots of, now these are all three-dimensional, right? But I'll point out, furthermore, the two-dimensional fluid flows also pretty easy to talk about. Surface water being sort of obvious, right? Rivers, rainwater on a parking lot, right? Flows around two-dimensionally. And I want to pose that animal migrations, if you think about it, kind of fluid-like. You know what I mean? Especially the smaller the animal is. It's a lot easier to think of, the flow of bacteria through a petri dish or whatever, right? Because they're so small, we think of them as, kind of like a fluid. Maybe harder to think of bison as being a fluid, right? If you think about it, all fluids are made up of particles. It's just that they're really small or maybe they're bigger, but whatever. Large collections of particles that are all kind of moving together very naturally can be thought of as a fluid. Okay. Pausing here for questions. Everybody buy it? Okay. All right. Okay, so I want to do a computation now from a fluid point of view. I'm going to assume that I've got a vector field that's representing the velocity of the fluid. Again, that's, think about air in this room, and if you wanted to represent the fluid flow at any given point, the air at that point at a given moment is moving with a certain velocity. So for every point you have a vector. That's a vector field. I emphasize this is not the only way to use a vector field to represent the flow of a fluid. I'm going to show you another one in a few minutes. But for the moment, vector field represents velocity of the fluid at the given point. Okay. Now, I'm going to entertain the following scenario. Suppose I have a flat, just to keep it simple, small flat piece of area, right? In order to describe how big it is, well, the area A, right? But in order to describe how it's oriented, I'm going to talk about its normal vector, and I'm going to insist that that be a unit normal vector, just to make the calculation go more nicely. Okay, so there's my little piece of area, and I've got this vector field. Let's see here, I'll use blue for the vector field. Keep in mind that the vector field represents velocity of the fluid, so there's my fluid flowing along. Now you could imagine with an area oriented like this and fluid flowing like this, I mean, there's going to be a certain amount of fluid that flows through that area per unit time, right? I mean, the vector field itself is in units of velocity, distance per unit time, but how much fluid, what's the rate that fluid is flowing through this area? How much water is coming out of your water hose? That's volume of fluid per unit time. Right? So that's what I want to try to get my hands on, given this scenario where I know the velocity of the fluid and I know a piece of area. I want to talk about what is the flow rate, volume per unit time of fluid passing through this area. Everybody on board? All right, so here we go. I'm going to start off by computing the volume of this parallelepiped here. This is the parallelepiped of, fluid that has flowed through my green area in a given amount of time, delta t. Right? In other words, if you start your stopwatch and watch the fluid flow through that area, and then you stop your stopwatch some amount of time later, there will be a parallelepiped worth of volume that has flowed through. Okay, so let's compute that volume. Old news, the volume is, as I have here, it's this height times the area, right? Height times area, right? Everybody remember that formula from high school geometry? Okay, cool. What is that height? Well, okay, to get my hands on the height, I need to think about this vector over here. I'm calling that D. Displacement, of course, by the way, it's exactly the same as that vector and this vector. It's all the same vector. I just, I drew it over here instead of over here because my picture's getting a little bit crowded, cramped over there. But exact same vector. I claim, for your consideration, that height is the normal component of that D vector. What do you think about that? So looking at let's see here. Well, looking at this part of the picture, right there, the height is the normal component. Of that displacement vector. Satisfactory? Everybody's good? Okay. All right. Let's see here then. What else do I need to say? Well, I can compute that component. Components are computed with dot products. Right? Keeping in mind, very importantly, that this in normal vector is a unit vector. And so don't have to divide by magnitude because the magnitude's 1. Okay, cool. All right, what is this D vector, though? How am I going to get my hands on D? Well, let's see here. This D, well, that represents, the reason I called it D is because that's the displacement of fluid. That's how far the fluid itself has moved in this amount of time, delta T. right? So displacement is velocity times time. What do you think about that? Everybody good? Okay. All right. So there's a lot of little details in here. Yeah, question?
I just want to know, is like calculating d, would it be the same thing as just finding the unit vector for f of x and then just multiplying it by t?
Well, the thing you got to keep in mind is that the vector field f doesn't just tell you what direction the fluid is going, it's also telling you the speed that the fluid is going. Yeah, so you really need the whole vector field. So I guess if you wanted to take the unit vector direction of f and then multiply by the speed, which is the magnitude of f, and then multiply that by delta t, sure, same, but it's literally the same calculation.
Okay.
Yeah, is that satisfying? Yeah, cool. Anybody else? All right. Okay. So yeah, lots of details, but now let me get rid of all of the clutter here. Altogether, keep in mind, my goal was to figure out the flow rate, volume per unit time. And, well, we computed volume and found out that it is a multiple of time, and so volume per unit time is what you get when you divide and take a limit, I suppose. And volume per unit time, then, is this thing. It's F dot N times the area A. And this expression, F dot N times area A, is called flux. Ends up being very important, shockingly important in understanding, a lot of the stuff that we're going to do in chapters 6 and 7. So this is a little bit of foreshadowing. Okay. The notation that we use to represent flux is a capital Greek letter phi. That's pretty standard. My assumption has always been that phi for flux, right? It seems like a natural choice. And capital to avoid the confusion with the spherical coordinate. Okay. All right. So now this example, I want y'all to use this as a template for an exercise that I'm going to leave as exercise for y'all to do on your own. By the way, I am very happy if you want to work in a group on this. Team up with your study partners, whoever you like to study with, and of course, I'm also happy to help if you come to office hours if you get stuck and don't know how to proceed on this. Very understandable, no problem. Then come ask me in office hours. And here's the exercise. Let's suppose that I represent the fluid flow in a different way. Let's suppose that instead of the vector field representing velocity, suppose it's density times velocity. And now, just intuitively, before we go on with the actual question, why would that make sense? In what way would it be natural to multiply velocity times density? And, well, let me go to the animal migrations metaphor. You could have a flock of birds flying along, right? And the thing is, how fast they're flying is not the whole story as to how many birds per unit time are passing through, whatever surface. It matters how many birds, how tightly are the birds packed in. If you have 50 birds per cubic yard and they're flying 15 miles an hour, that's a lot of birds. You're getting a lot of birds flying over the line or whatever, however you're keeping track. If you have one bird per cubic yard flying at the same velocity, that's just not as much bird flux, right? Yes, it's flying the same speed as the other birds, but it's just the one bird. You're not getting a lot of birds per unit time flying over the line. So, how much of your fluid, how many birds, how dense is the liquid, what have you, how concentrated is the pollution, right? Should be part of the story of describing how that fluid is flowing. And so that's why, in many cases, we insert a factor of density, lowercase Greek letter delta, by the way. and represent it like that. So that being said, here's the exercise that I want y'all to take a shot at. Suppose that your vector field is this. Show that this same expression, flux, that previously represented volume per unit time. Now, that same expression, flux, doesn't give you volume per unit time, it gives you mass or quantity of fluid per unit time. It's not dV/dt, it's dm/dt. So, I think it's a really nice exercise. The way you're going to do it is mostly just copying from this example here. The big, let me get you started. The big difference is that instead of computing an amount of volume, and let me pick a better color, instead of computing volume per unit time, you're going to compute mass per unit time. Mass, of course, is volume times density. And then that factor of density will carry on down here, and then you got to figure out what happens at the end. Anyway, it's something to think about, and I think it's a good exercise. But notice it is extremely analogous to this first example. Okay, so like I say, good exercise. Give it a shot. If you have trouble, talk to friends. If you still have trouble, come to my office hours. I'll show you the whole deal. Yes.
So would density be a function of position if you have vector?
Yes, absolutely. Yeah. So not all fluids are uniformly constant density. That's right. Yeah. Birds being a good example. Yeah. Totally. On the small scale, though, so recall here that we are talking about a small piece of area here. And on small scales, we do assume that it's constant. It's close enough. Yeah. Does that make sense?
Yeah.
Cool. Okay. So yeah, if you have any trouble with this exercise, come talk to me in office hours. Okay. Now, this next page, I want you all to see some weirder examples. I want to recognize certain ugly realities about fluid flows, that they are not always simple. And so anyway, this is, I think, a good exercise. Suppose you have a light source. Here's a light bulb right there. And what do light bulbs do? Well, they create light. You may know from physics, high school physics, that light comes in the form of little particles called photons. Right? So what do light bulbs do? They generate this fluid. Right? There's a flowing fluid of little particles called photons, and that's what it means to have the light on. Okay. Is that satisfactory? Everybody's happy on that? Okay. All right. So, among other things, I mean, as the fluid shoots out of this light bulb, as the photons shoot out of this light bulb, going every which way, at this point over here, for example, a photon that came from this light bulb is going to be going to the right. Okay. Here's the thing. Sometimes a room has more than one light bulb in it. And so, for example, here is another light bulb at a different location. And it's shooting out photons every which way as well. Among other things, it's shooting out photons when they get to this same location are going a different direction. So, given this scenario, if I were to have two light bulbs, and by the way, I've got a couple rooms in my house with two light bulbs in them, right? So, very common scenario, how would I describe the flow of photons in this case? I can't say, just use the velocity. Which velocity? What do I like? Atom or something? That sounds kind of plausible, actually, but are we sure about that? It's not clear. Right? Hard problem to deal with. Let me show you how we deal with this, and that is we basically use the idea of flux to kind of reverse engineer the idea of the vector field. And so I may not be able to tell you what the velocity of particles is at any given point, but given any little small flat area, just like on the previous page, given a little area, I can count photons. And you say, how many, well, given this piece of area, oriented however it might happen to be oriented, I just keep track of how many photons are flowing through that area. Does that make sense to everybody? With the idea that there is a positive direction through the fluid, and I guess I should have said that back here, that another role that this normal vector plays is it defines what we mean by the positive direction through the surface. So a fluid flowing this way creates a positive flux. But if you had a different fluid flowing this way, for example, notice it's going the opposite direction of the normal vector. And you can see right here in the formula that the normal dot, the vector field here, would be negative, not positive. Because the angle there is an obtuse angle. Is that cool? Everybody see that? Okay. So think of it as that the unit normal vector describes what is the correct or the positive, however you want to think about it, direction through the surface. Okay. So all right. Well, if I can compute dmdt or measure dmdt, then I could ask, well, what is the vector field that makes this formula work? And this is a pretty reasonable way to define a vector field in such a scenario. Normally, we have a vector field given and understood, and then we compute dmdt from this formula. But we're going to turn around backwards. I can compute dmdt anywhere I am. And there will be a unique vector field. That's a claim. I'm not going to prove it. Plausible claim, though. There will be a vector field that will match up with those fluxes by way of this formula. Okay. All right. So I want to show you an example of how we can use this, and this will be the last thing we'll do today. Weird scenario. We have a uniform ball of glowing gas. I know that's strange, but let's just pretend. By the way, not that far off from what the sun is. Right? Big ball of gas. I don't know if it's uniform, but in this scenario, let's pretend it's uniform. Okay. All right. So every particle in this cloud of gas, every particle is shooting off photons. After all, it's a glowing gas. Right? So that particle is shooting off photons. But here's the thing. So is that particle. It's also shooting off photons. And so is that particle over there. It's shooting off photons. And this one and that one and that one. And you get the idea. So at any given point, if I were to look, let's say, right here, very hard story to say, what's going on at that point. At that point, there's photons going every which way. Because there are photons at that point that came from all sorts of other different locations. So, nightmare of a mess, right? It's very hard to talk about the vector field. What's actually pretty easy to talk about is the flux. So, if we were to ask the question, given a little ball over here, and looking at its boundary, looking at this boundary sphere, if I were to ask, how many photons per unit time are passing through that ball, that sphere? And here's how easy the answer is. For every particle inside the sphere, shooting out photons every which way, how many of those photons go out of this sphere? All of them. Real simple answer, just all of them, right? If you're a photon that got generated inside the sphere, you're going to shoot right on out, and you contribute to the flux outward through that sphere. So, proportional to volume. More volume, more gas, more photons, more flux. Now you may say, yeah, but what about the stuff over here? What about this particle here? That particle, that's shooting photons out as well. Doesn't that contribute to the flux? Actually, it doesn't. Because every photon originating outside of your sphere, well, yes, it does shoot out of this sphere over here, but it also shot in just prior. So, in a steady state situation, the number of photons from here that are going out of the sphere is exactly the same as the number of photons that are going into the sphere, exactly, and they cancel. So that's just 0. So really wonderfully convenient result here that that even though I can't understand the vector field immediately, I can understand the flux through little spheres actually pretty easily. It's going to be some constant proportional to the volume. More volume, more gas, more photons, more photons, more flux. Okay, and we are out of time, so I'm going to have to pick up here on, soon. So I'll pick up here, anyway, let me say soon. Okay, see y'all later. Have a good one.